Okay, now we're going to talk about the parallel axis theorem. This is something that comes up all the time, and it comes up in the other chapters, but we're going to need it again for this chapter. So what does this mean? Well, consider you have the moment of inertia I of an area. So here we have our potato blob, right? But it's not centered on the axis that you're concerned about. It's instead you're trying to figure out the moment of inertia about some arbitrary axis AA. Okay, how do we do this? Well, what is I? It's integral of y squared dA, right? So it's integral of the distance to the point dA. But what is this y? Well, this y has a certain distance to the centroid, and then plus an additional distance to the dA. So y prime plus d, this is y, so you square that, square dA. Well, then when you multiply that out, you end up with y prime squared dA plus 2d integral of y prime dA. Remember, d is constant, right? So that's why you can do this, because d is constant, plus d squared dA. Okay, so if the axis, BB, so if you put this axis through the area centroid, it's in other words a centroidal axis, right? Then this term right here is y prime squared dA is what we're going to call I bar, right? It's the moment of inertia through the centroid of the axis. And then d squared integral of dA, this is constant, so it's just integral dA, so it's just a times distance squared. Okay, so that takes care of this term. That takes care of this term. But we have something that we remember, that the first moment qx is defined as integral of y dA, right? But not just that, at the centroid, we know that qx and qy is 0. So therefore, when we have this y dA term, or this y prime dA, because this is what we're talking about here, this term is 0 only when y prime passes through the centroid. So if you're doing the parallel axis theorem, it has to be with respect to the centroid. You can't just pick any two random points. It has to be with respect to the centroid. But if it's with respect to the centroid, that term goes away and I becomes I bar, in other words, the centroidal I plus the area times the distance squared. And that is the parallel axis theorem. Okay, so let's do some examples, just kind of real quickly, some examples here. Whoa, wrong direction, my bad. Okay, the moment of inertia. Let's figure out the moment of inertia IT of a circular area with respect to the tangent axis, right? Okay, so we want the moment of inertia with respect to this axis. Okay, so any I, right, is I bar, so the centroidal moment of inertia plus area times distance squared. Well, you look up the centroidal moment of inertia for a circle, it's 1/4 pi r to the fourth, right? So that is this term. And then what is the area of a circle? It's pi r squared. And what distance? Well, you're moving it from here to here, which is r squared. So it's 1/4 pi r squared plus pi r to the fourth, so that's going to give you 5/4 pi r to the fourth. Okay, let's look at another quick example. The moment of inertia of a triangle with respect to centroidal axis. Okay, now here, this is we're trying to find the moment of inertia at some other point, right? Here we're trying to find, hey, what is the moment of inertia at the centroidal axis? And so what's special about that? Well, it turns out that we know the moment of inertia with respect to this axis. What is that? It's 1/12 bh cubed, right? I think. Yep, there we go. So IAA is IBB, right? It's the centroidal axis plus the distance times the distance squared times the area. But we actually know this. We're looking for this in this. I'm sorry. We know this, but we're looking for that, right? So we need to solve for this. So how do we do it? IBB prime is IAA prime, and then you bring this over to this side of the equation, minus AD squared. Well, again, we know this. It's 1/12 bh cubed, so we're good there. Minus the area, so the area is 1/2 bh. That's the area of a triangle, right? And the distance squared. Well, the distance from this axis to the centroid is 1/3 of the height, and so the distance 1/3 of the height quantity squared, and so that gives us 136 bh cubed. So you'll notice this moment of inertia with respect to its centroidal axis is quite a bit less than the moment of inertia with respect to this axis here. Okay, so those are some examples going through and working out a circle and a triangle. Well, it turns out that there's you have a table. It's a table in your book, and when we're dealing with composite areas, right? So a composite area, when we talk about that, we're generally talking about when you have a bunch of known areas. Okay, so when we're dealing with a composite area about a given axis, in order to find the moment of inertia, you're going to add up the moments of inertia of the known things. And so you're going to say, hey, if you have a circle and say a half circle, a dome on top of a rectangle, right? You figure out the moment of inertia with respect to that and the moment of inertia with respect to that. And so you'll notice on some of these, you have the bars, right? This is a great example. On a rectangle, you know that through the centroid, the moment of inertia is 1/12 bh cubed, right? But through this axis, through the IX, it's 1/3 bh cubed. Make sure you're using the correct one. They are different, obviously. The one's 4 times smaller than the other, okay? So you don't just pick one. Use the appropriate one for that. Same with for a triangle, right? Through the centroid is 1/36. Through the bottom axis is 1/12. You'll notice on circles, they don't necessarily give you, all these different places. So here on a circle, you get the bars, but you don't know what it is through here. You'd have to calculate it if it was at some other point. Half a circle. You'll notice that half a circle, it's actually kind of interesting. Do you know the bar? You do not. They actually give the value through this point right here. So if you needed to do the parallel axis theorem, which I think there's a homework problem all sorts of times when we're going to do this, you actually have to figure out what it is here before you then go and offset it to some other point. So that's an important thing to note. Quarter circle, same deal, and then ellipse. So these are just examples given throughout you have them in your book, this table in your book, so please go ahead and use it. Now, the slightly, I don't know if more interesting is the right term, the other one, if you will, is moments of inertia composite areas of kind of standardly used shapes in civil engineering type applications. We have W shapes, flanges, I-beams, H-beams, right? So there's some standard things, and you're going to have a couple homework problems where you actually use these things, where you're going to say, hey, there's a S10 by 25.4. Well, hey, it's right here. Well, what is the moment of inertia? You could integrate that if you knew the equations, but don't, because you're going to come and say, hey, the moment of inertia in X is 123 inches to the fourth, and in Y is 6.73 inches to the fourth. So this is, and then so you have your English units table and you have your SI table, and again, these are in the book. If you need this for the test, you'll have these tables as appropriate in the if you need them for a test. But for the homework, go ahead and use your book for these tables. So let's do a couple examples of these to help hopefully clarify things a little bit. We're going to do example 9.4 and 9.5.